Hello everyone, welcome back. The last few classes we are discussing about the G-SQL resolving simulations, and we discussed about the DNS and LES and how they differ in terms of computational cost and compared to RANs. Okay. So, in the last class we started discussion about LES, and we said that in terms of energy spectrum, okay, if this is your energy spectrum, okay, this is E k versus k. Okay, a good LES is the one which resolves at least 80% of the turbulence kinetic energy, right. So, if this is 80%, let us say, okay, so the LES should resolve this region, okay, and you can use a model for this region which is mainly for the dissipation, right. So, this is one check you can do if you are performing in LES. You can we discussed about how to calculate this resolve energy, resolve kinetic energy, basically the KRES, okay, and also the KSGS. So, SGS can be directly calculated if you are using an explicit LES. You can directly be an output of the model that you are doing, model that you are using, and KRES you can calculate based on. So, you have this U V bar and U bar V bar, and just you can subtract them and you will get this U prime V prime bar. Okay, we had this derivation yesterday, and you can calculate what is the ratio of KRES by KRES plus KSGS or K model, whatever. So, and if the value of this is greater than 0.8, then it is a good quality LES. Okay. So, this you can check well, you are basically you have already performed LES. The other thing we discussed regarding LES is like how do you decide the grid size before starting LES. So, typically what you do, you perform a range simulation, right, and from the range simulation depending on what model you are using. So, let us say you use the K epsilon model. Okay. So, you can calculate the length scale from this K epsilon model, and how do you calculate that? Remember like we have discussed in the eddy viscosity model, all these models have this new turbulent or new eddy, okay. Eddy viscosity is basically some factor of L naught into U naught, okay, some length scale and some velocity scale, because this its unit is meter square per second and this is meter and this is meter per second, right. So, if you are using a K epsilon model for example, then this thing will be, so your L naught will be I guess k to the power 3 by 2 by epsilon, and you can calculate it also because see k is unit of k is so meter square per second square, right. So, this is k to the power 3 by 2, that will be meter cube by second cube, right, and epsilon is the dissipation rate. So, how much energy is being dissipated per unit time. So, meter square per second cube, right, meter square per second square is the kinetic energy and per second of that. So, if you do k to the power 3 by 2 by epsilon, that will give you the unit which is meter, which is the length scale, right. So, you can calculate the length scale from the model, and what we also discussed that you can have an integral length scale. So, what is the meaning of integral length scale in this case? So, that is a length scale at which the average of kinetic energy is obtained. Okay. So, this can be your this can be your 2 pi by L naught, right, and L naught you can calculate from this from any turbulence model. I have given example of K epsilon model, but you can use K omega or any model that you use based on eddy viscosity model that will have this length scale. Okay. And what we also argued that typically how do we find out if a mesh is good enough for LES is that we should have at least 5 elements to resolve the integral length scale, and when it is that, it is likely that it is going to resolve this 80% of energy. So, if we are using 5, let us say we have a scale which is delta, which is L naught by 5, right. So, this is my 2 pi by delta. So, delta is the length scale for LES, okay. And we are arguing that this typically resolves 80% of kinetic energy. Now, delta you also know from your grid, because typically delta is Cs into volume to the power 1 by 3, okay. And for the let us say if your mesh is structured, then this is Cs multiplied by delta x, delta y, delta z to the power 1 by 3, okay. So, this is some kind of determination of the length or your grid size, right. If it is unstructured, then you can use any method to calculate the cell volume, right. And Cs is a Smegmanovsky constant, which whose value vary from 0 to 1, and typically it is taken as 0.1, or you can some codes take 0.17, 0.2 and so on and so forth, right. So, you know the value of delta from your grid, okay. You know the value of L naught. So, from your range simulation, and what you can do, you can plot this L naught by delta in your entire region, okay. And you should see the regions where this value is less than 5, okay. Typically what we want, this L naught by delta should be greater than 5. If it is greater than 5, that means we have at least 5 elements in each integral length scale, and then the mesh is good enough for LES. And if the value of this L naught by delta is less than 5, then that is the region you need to make refinement, right. And you can do that, and this is how you basically decide the size of your LES grid, okay. So, typically because you do a range in range you perform in 2 dimensional framework, right. So, based on your 2 dimensional framework, you can also decide that if your grid is 3D, what is the value that you should use in the span-wise direction also, because you will get this minimum delta x delta y in 2D, and accordingly you can decide your delta z also. And it also depends how much variations you have in the span-wise direction. Some flows are nominally 3D, that means that the third dimension is for the turbulence to develop, but you can have the mean flow in 2D, that means there is no change in the mean flow in the span-wise direction. Okay, in that case you can relax the grid size slightly in the span-wise direction compared to what you have on the in the boundary layer on the face, right. But if the grid is if the flow is truly 3 dimensional, then you have to make sure that you are resolving in the span-wise direction very well, okay. So, this is what we discussed in the last class, okay. So, today we are going to discuss about LES equations. Okay, so, in the last class we had a very brief discussion about LES equation towards the end, when we said that like we had this like Reynolds stress or the Favre stress, we also have this subgrid stress in the large eddy simulation. And the only difference is that in the range we are using for the mean flow, here we are using for the actual flow variable, okay, which is u v w. And the second difference that we had is that in the Reynolds average noistic simulation, we use this turbulence model everywhere, okay. In the LES we want this subgrid scale model or the subgrid stress to act only on the grid size which is smallest grid. That means that okay, if you go to the cascade structure, right. So, it can resolve this grid and probably this grid, this eddy, right, but it cannot resolve eddy which is just fitting in here, right. And suppose the dissipation is happening at a scale lower than this, which is what typically happens in LES. In that particular case, what we need to do is that we need to do something so that the dissipation happens at this grid size, okay. And for that we need to basically increase your viscosity to increase the dissipation rate, and you have molecular viscosity and you will add some kind of this subgrid stress, okay, the viscosity for the subgrid stress. So, let us because there is a lot of analogy between the Ran's equation and the Elias equation in terms of this subgrid stress. Let us go through the derivation of the Elias equation systematically to see how these equations differ from the Ran's equations. Okay. Okay. So, when we think about Elias, so we can think about a sieve, right. For example, what you use to basically filter out anything, right. So, when you put something in a sieve, so the larger particles will remain, the smaller will go down, right. So, the Elias is in Elias also we apply filter. This filter may be explicit or may be implicit, in the sense that the grid itself may act as a filter, or you may put a filter a mathematical filter to basically filter your Navier-Stokes equations, right. In the most common practice, we do not apply explicit filter, and this is due to Smagorinsky, who said that your grid can be used as a filter, right. Because ultimately what we are trying to do is that for the smallest grid size, we want to basically model some kind of dissipation, right. So, even if you are using the explicit even if you are using explicit filter Elias, it is a good idea to basically go through how these equations are derived, okay, and the same concept will be useful even if you are using an implicit filter or an explicit filter. Okay. So, filter is basically a kind of a convolution operation, which is what is written here in G. So, if you have this phi can be any quantity, it can be u, b, w, p, rho, etc. Okay. In the incompressible flow, it is only u, b, w, p, and if it is flow is compressible, then we will rho as well. So, what it does, what this convolution operator or the filter does is that it acts on this function phi, okay, and it basically changes the nature of phi. Basically, it acts as a low pass filter. So, it will allow the low frequency, but it will not allow very high frequency. Okay. And it can be also written as so what we are doing, you are denoting the filtered one as tilde and the normal one as phi, right. So, this can also be written in a short form as G star phi. Okay. So, G is the convolution operator acting on phi to give you phi tilde. Okay. Now, these are some examples of the filter. So, one is for example, this box filter, okay, like this, or you can have the Gaussian filter, okay, or you can have the spectral cutoff filter. Typically, this box filter and the Gaussian filter are used in the explicit filter Elias approach, and all of these have this same function, that it acts on a signal, okay, and it removes the high frequency content. Okay. Without going to details, just let me show you one example. So, let us say this is your original signal, okay, this blue line that you see is an original signal, and below is the convolution operator, this is G x, okay, and this G x is acting on the signal, and you can see that as it acts on this signal, okay, and the region starts getting smooth. So, this is a box filter that is acting on this. Okay. So, this is already smooth because this the filter has already acted on that, and as the filter goes through this signal, and you can see that this becomes smoother and smoother, which is shown in the right side. Okay. So, this will become smoother and smoother and like this, okay, and at present it is in this region, right. So, here also it has made the signal smooth up to this point, and then as it goes through, you can see that it becomes more and more smooth, okay, and it basically loses the high frequency signal there, right. So, if you do truly a DNS, then you will resolve the original one, but in the case of LES, let us say if you are applying a box filter, what you are resolving is this signal. Okay. And I gave you an example of box filter, but the similar filters, I mean similarly you can think about the Gaussian filter or the spectral filter. And this is how in different filters work. Okay. So, this one is for DNS. Okay. Let us say if you are not using any filter, and if you use a cutoff filter, this is the red region is what you see when you use a, you basically cut off at a particular frequency, okay, or a wave number. So, you can see that the energy is just going down at the place, okay, and the green one is the top hat filter, what you see here, this is the top hat filter, okay, and then the blue one is the Gaussian filter. And this is what we have been discussing when we are talking about LES, that when you have this EK versus K, okay, you are not resolving everything, but you are cutting off at certain point of time, and as long as you ensure that it is capturing 80% of energy, this region does not matter, because this is primarily responsible for the dissipation of energy, which does not participate in the key dynamics of the flow. Okay. So, now that we have filtered our variables, okay, so we have filtered our variables u, v, w, p, etcetera. Okay. So, we can write the full variable or the full signal, okay, phi is equal to phi tilde plus phi prime. Okay. I want to differentiate here, this phi prime is not like what we had in the range simulation. Okay. So, range simulation, these were like all turbulent fluctuations, phi prime in the case of range. Okay. So, these are basically turbulent fluctuations. Okay. In the case of LES, it is only in the subgrid scale. Okay. It is not that all the turbulent fluctuations have been captured here, okay, because some of this turbulent part is also there in phi tilde. Okay. So, this is only the subgrid scale fluctuations. Okay. And now, going through the similar argument, if you recall, we had discussed the properties of a Reynolds operator, right. So, what were the properties of Reynolds operator? For example, if you have a mean, okay. So, what was the Reynolds operator? If you think in terms of incompressible flow, okay. In Fabre we had the rho also, but in the incompressible flow you had basically x t dt, okay, and you basically started t equal to, I mean, t naught to t naught plus t, okay, and I think divided by dt, okay, t naught to t. Okay. So, this was the our Reynolds average or the time average, okay, and we had discussed about some properties that if it is a good time average, the mean of the fluctuation will be 0, okay, and the other thing was that if you take the average of average, this is nothing but the average, okay, and then we had like if you have this du bar by dx, because a linear operator, you can write it du bar by dx. Similarly, the summation will commute, if you have phi plus psi bar, it will be phi bar plus psi bar, right. So, like this, this is for range, and like this we can have some properties for the filter also, for the LES filter also. And what are the properties? So, one thing is that the integral of this the filter gx ds equal to 1, that means that if you have a constant a and you apply this convolution on that, okay, you will get the same value a, okay, it will not change. And like the Reynolds operator, it is also, you can if the apply the filter on a summation of two variable, you can break it, or you can rewrite it as the, you can basically commute the operation, you can first apply the filter and then do addition later. And similarly, if the operator is linear, you can write it like this. Okay. It is different from the Reynolds averaging, and the reason is because we had discussed earlier that our fluctuation u prime in the LES is not as the u prime for range. Okay. It is not a U prime from variance, this is a turbulent fluctuation and this is the LES fluctuation, okay, LES or SGS fluctuation, that would be a proper term. Okay. Okay, and you can show it mathematically also using this filter. So, let us say if you apply this filter twice, you have a variable phi and apply this filter twice, then you are basically this convolution is this is G convolution operation and then another convolution on phi, and which is not equal to just one convolution. So, here we had like a U bar and then you take another bar because it is already mean. So, then it will be equal to just the mean, okay, no matter how many times you are applying this averaging operation. But here in the case of LES, okay, once you filter and if you filter again, it will be different from so the a variable which is filtered twice is different from a variable which is filtered only once. And if you use this property here, okay, this what is phi prime, okay, so phi prime is basically phi minus phi tilde, which is phi minus G into phi, right. So, this is a variable, okay, and then you take the apply the convolution on top of that. So, that will become G into phi minus G into phi, and since this is not equal to this, okay, so this value will not be 0. Okay. So, phi prime tilde will not be 0. So, is in general the LES filter do not basically satisfy these two properties. Now, that we know the filter, we can basically derive the equations, but before that I just want to discuss a little bit about the implicit and explicit filter. So, in the implicit filter, okay, we have discussed about the box filter and Gaussian filter and cutoff filter and so on and so forth, right. But they will not be basically explicitly used while you are writing a code, okay, or while you are doing the simulation. And what we assume that our grid itself is the LES low pass filter, right. So, the grid size acts as a filter, okay, and this is a more common approach like an Ismay-Gorensky and all, okay. So, where there they use the implicit filter, but some researchers also use an explicit filter where they basically typically use the box or Gaussian type, and this is applied to the grid, okay, and both have got some advantage and disadvantage, okay. And in terms of advantage, what you have in explicit filter is that you basically have the control of what is going through your sieve, right, and you know what is happening there. But what is a disadvantage in explicit filter LES is you basically lose some of the numerical resolution. So, your scheme has got certain resolution, but you are applying filter on top of that. So, you may lose some of this resolution, okay. But this is I mean more tedious to write. If you in terms of developing code, the explicit filter code is slightly tedious to write, but implicit you make a grid and you ensure that the grid satisfies the property that we discussed earlier, and that grid can be used as a low pass filter. Okay. Now, let us go through the derivation, and like we did for the RANS case. In this case also, first we will derive for the incompressible and then we will make some comments about the compressible flow. Okay. And why we do that? Because as we know from RANS is that in the case of compressible flow, your rho also becomes a variable, and when you have the conserved variable like rho u, and if you try to basically break it in terms of fluctuations and the mean flow, you will get terms. Okay, if you have a rho u v for example, okay, you get triple product, and there are many terms which are basically which complicates the equation a lot, right. So, that is why it is easy to visualize in compressible flow where your rho is a constant and u v are basically you can easily handle, okay, two variables. Okay. So, this is your Navier-Stokes equations. Okay. Once again, this is your temporal term, then you have advection term, the pressure term and the stress term, and in this case tau I j will be nothing but nu del ui by del x j, okay. And that is why this term will become in the vector form del square u, right, for the incremental flow. So, if we apply filter on this, so we are applying filter on this Navier-Stokes equation. Okay. So, basically you are multiplying this by g. Okay. So, what will happen? The first term will become, you will get a filter here. Okay. Here you get a term which is u I u j and filter on both of them. Okay. And then p will get a filter. Okay. And then finally, you will have a filter on the tau I j term, the shear stress term also. Okay. So, which is basically nothing but nu del square u filter, right. Now, what we will do, we will rewrite this term, okay, u I u j tilde, okay. And what we will do is that see, we are solving for u I tilde and u j tilde, okay. So, we will rewrite this expression in terms of u I tilde and u j tilde separately, right. So, if you want to do that, then it can be written as u I tilde u j tilde and plus u I u j tilde minus u I tilde u j tilde, right. Now, this following the Reynolds stress argument that we had in RANS, we can write this in terms of the stress, okay. So, that is your subgrid stress, okay. Because we are dealing with a fluid flow problem. So, these forces basically lead to some stress and they can be expressed in terms of our known gradients, the velocity gradients, and that is why it is easy to write in terms of the subgrid stress. Okay. So, that is how we will do. So, this will become tau I j s g s, and if you take that out and put it back here, okay, what you will get is the momentum equation for your incompressible LES, right. So, you have this term tau I j tilde and then you have tau I j s g s, and what we will do in the next class, we will derive about the derive compressible LES equations, and we will also see that how we can apply this our eddy viscosity model in this tau I j s g s, okay, tau I j s g s, okay, and this can be written as nu s g s, okay, multiply by some kind of your your gradient field, the velocity gradient field, okay, like we have done for the RANS, okay, maybe there will be rho here, okay. So, this we are going to discuss in a next class, and we will see that for the compressible flow also we have basically the similar arguments. We will do the Favre averaging because the density is also a variable there, and we will have some more complicated terms. Of course, we have to have the energy equation also, but that is what we are going to do in the next class. Okay. Thank you very much.